Hi guys, so I want to go over the homework, the first part of the homework on 10.2. I gave you some additional exercises. I'll look at them right away, but first I want to do the other one that comes from the textbook. So number 5 from the textbook, and there was can a simple graph exist with 15, so there are 15 vertices of degree 5. And the question is, can it exist? And the answer is, well, how do we find this out? And I hope the same, we will see for the additional questions, the same issue comes up. We need the handshake theorem. So remember the handshake theorem. It says that, and we're going to use it just for undirected graphs. The number of edges, twice the number of edges, is the same as the sum of all the degrees of all the vertices. Okay, and a corollary or another theorem, we had a second theorem, theorem 2, that we called, was that the number of edges, the number of, not the number of edges, the number of odd degree vertices, that number, we don't know what it is, but it is an even number. So these are the two theorems that you use in handling this problem. So you see already that the second one is violated here. The number of odd degree vertices has to be even, and here we're saying there are 15 vertices of degree 5. That's an odd number. So no, because this should hold. Okay. There is also a second reason. I mean, you can also use the handshake theorem for the same reason, actually, because remember the second theorem that derived here follows from the handshake theorem. Look at how many. What's the sum of the degrees here? If there are 15 vertices of 5 degree, so what would this number be? So in this case, this number would be 5 times 15, right? They all have degree 5. There's 15 of them, so this would have this altogether is 75. This can never be an even number. So for the same reason, we have an answer no there. Okay, so let me get rid a little bit of this here and also these numbers here, because so this I want to now use also the solve the other problems. So a graph has four vertices of degree 3 and 2 of degree 2 and 3 of degree 0. Now, as we have seen already, it's just I cannot just stipulate any kind of configuration. Like, for instance, the configuration of 15 vertices of degree 5 does not exist. So you could question, does there exist a graph of 4 vertices of degree 3 and 2 of degree 2 and 3 of degree 0? And the answer is yes, it does exist. It's not obvious that it exists, so I have to show you that it exists if I want to. But let's assume that I've been truthful here. I gave you something that possibly exists, but still the question remains, how many edges does this graph have? Well, we use this theorem here, the handshake theorem. So let's calculate in other words, what we have to calculate is this thing here, right? So what is it? Well, we have 4 vertices. So the vertices are divided in our scenario here in 3 types. Right? The ones of degree 3, the ones of degree 2, and the ones of degree 0. Now there are 4 of degree 3, so they contribute. This number is then 3, and there are 4 of them, so that the contribution would be 4 times 3, right? Plus, how many are there? Are 2 of degree 2, so 2 of them have degree 2. So in this sum, there will be twice a number 2 coming in, and then there will be 3 times the number 0 comes in. It's of course a little bit silly to write it, but let's do it. 3 times 0. So this is this total sum, and that is 12 plus 4 is 16. And this is equal to 2 times the edges, so this means that the number of edges is 8. Okay, and if you wonder that such a thing actually does exist, I'm going to refer you to the textbook, see exercise number 25, where there is such a graph that has 4 vertices of degree 3 and 2 vertices of degree 2. Now, it doesn't have 3 vertices of degree 0, but that's very easy, right? That is just putting 3 points extra vertices there without any edges. That is always possible. So it does exist, and it's not a, I mean, you can draw it yourself. So that was for 1. So what about 2? Can there be a graph with vertices A, B, C, D, E such that the consonants have degree 3 and the vowels have degree 2? So what if you could try, if you one thing to show this is by drawing such a thing and say, here it is. Okay, so let's think a little bit about what are we saying here. So we have the constant, there seem to be 2 degrees. So let's look at the degree 3 ones. Which are the ones of degree 3? Well, I'm saying the consonants. What are they? B, C, and D, right? I hope that is clear that these are the consonants in those, among those 5. And then we have the ones of degree 2. These are A and E. So there are 3 of degree 3 and 2 of degree 2. Why is this not possible? Because of this here. The number of odd degree vertices has to be even. There are 3 here that's not even. So this thing violates, so it violates it, so like this contradicted, right? The fact that it should be even. So such a thing cannot exist. So the answer here is no. In a computer network, any computer is connected to exactly 5 other computers. If the network has 30 connections, how many computers are in this network? So, okay, we clearly have, again, something about the degree. So what's the degree of a computer here? Let's call them C. In any computer is connected to exactly 5 other computers. So the network, of course, is there's an edge if there is a connection. That's, I hope, clear. That's what a computer network looks like, right? So I'm saying exactly there are 5 other computers. So what I'm saying, this is exactly what I'm saying. Every computer has degree 5. Oh, okay. So now we can calculate this quantity again. So now this quantity, let's calculate this quantity. It's summation of all the vertices times, and each has 5. Okay. What else do I know? I know how many connections there are. There are 30 connections. What does that mean? What is a connection? Well, a connection is exactly an edge. So I'm telling you there are 30 edges. So I know that the number of E is 30. Ah, but this is equal to 2 times E. So in this case, this is 60. Okay. Now, what is this equal to? Every vertex has degree 5. So we adding 5 plus 5 plus 5. How many times? Exactly as many times are there vertices. So this is the equation I get. 60 is 5 times V, and therefore I find that V is 12. Okay, so that was 3. And then 4. A graph has n vertices of degree 3 and 1 vertex of degree n. Again, you could say, I don't believe that exists. I'll show you. How many edges does this graph have? Okay, so let's look at this now. Again, we are calculating the same quantity, and for sake of not having to scroll down all the time, let me do it, solve it here. I don't need this guy either anymore, so I'm going to erase it. It's the last question, right? So I don't need all this thing in the row. Okay, so let's calculate this here. Now, there are 2 collections of the 2 types of vertices, the ones of degree 3, and there are n of them. So we have the summation of x in V of degree 3, let's call it that one. Okay, and each of them has degree 3 plus 1. Well, okay, why am I making it that way? I'm sure everybody sees it, so let me say it quicker, right? There are n vertices of degree 3. So in this sum, the value 3 appears exactly n times. So we have 3 times n, and there is 1 more vertex, namely 1 vertex of degree n. So that adds with another n. And that is equal to 2e. Well, this is equal to 4n. So divide both sides by 2. You see that the number of edges is exactly 2n. Now you might say, how do I know that such a thing exists? Well, here is an example. An example of such a thing is the wheel. Why is that? Look, the wheel, like this is how a wheel look like, right? So we go around, we get all this number of, you first make a cycle, This is Cn. Yeah, okay. So this is supposed to be Cn, right? So of course I cannot draw Cn in general, so I'm going to put some dots here. So that's how Cn looks like. So how many edges does Cn have? Well, if you think about it, it's n edges, right? So it's clear that there are n edges Cn. So let me perhaps say that. So Cn has n edges. It also has n vertices. So it's n edges and n vertices, right? It's not impossible, right? Yes. Now, that's not the wheel. What's the wheel? So I'll do it in a different color that you see that something new happens. So here I'm going to put in one more. Remember, Wn has n plus 1 vertices, namely the n vertices on the cycle, and then you dry the spokes from the inside part. And so this goes on again, and then here. Now, how many of those do I have? Another n, right? Because there are n outside vertices on the cycle, and so I am going to draw n more. So I have n edges here, another n edges here, so altogether 2 n edges. But look at the degrees now. Let's look at the degrees of this thing. What is the degree of anything on the let's take any point here. That's very symmetric, right? So everything is the same here. They all have the same degree. 1, 2, 3. So this has degree 3. Sometimes one writes the degree on above or next to the node. So it's a bit confusing. Sometimes when one writes the degree there, it doesn't mean that that's the node, but sometimes it's the name of the node. So be a bit careful of that. And now, what's the degree of this guy? Well, I just said it. I'm drawing n edges from that middle guy and spokes, right? So the degree is n. So we have n vertices. There are n of these outside guys, right? That's the whole presumption of Cn of degree 3 and one vertex of degree n. So that's Wn has that property, and we also saw already that Wn, just counting it in a different way, has 2 n edges. Okay, but this is without knowing that it was Wn, we still could find out how many edges there are. Okay.